design. Well, welcome. And this is a webinar courtesy of EasyPower regarding the IEEE standard 1531-2003. My name is Pablo De Jarmy. I'm Mexican. Right now I'm in Mexico. And this standard is a guide for application and specification of harmonic filters. This webinar will last about 1 hour. If you have any questions, I will gladly answer them at the end of the session. So, what are the objectives for the webinar? We will review and understand the IEEE standard 1531-2003. We will determine the proper sizing of harmonic filter elements, which we will see them shortly, according to the standard's recommendation. And we will sort of establish a procedure for harmonic filter components specification. Now, designing a filter is something that takes some hours to learn to do. It's not the scope of this webinar to fully teach you how to design a filter, but I guess that most of you already know how filters work. Nonetheless, the scope of this webinar is regarding the standard. This standard, as any IEEE standard, is not a rule, is not a law, is a general set of guidelines, and this particular standard is a guideline for passive filter design. Obviously, active filter design is way out of this standard because it involves electronics, power electronics. This is not. And this webinar will only reference notch type filters. I'll get back to that in a minute. Why? Because these are the filters, the simplest filters to design. They have the least amount of elements. And other elements have design criteria that are beyond the scope of this webinar. Now, this standard is good for 50-60 Hertz design and harmonic multiples up to 1 kilohertz. That means that if you're looking for a guide to design filters in electronics, which tend to deal with the kilohertz, with the megahertz frequency, this is not the guideline. This is just for power systems. The design considerations change a bit when you deal with very high frequencies. Now, this standard includes low voltage and medium and high voltage filters, but this webinar will be limited to the low voltage filters. Nonetheless, the design principles are pretty much the same, and if you get the point of the low voltage, you can get to the high voltage, and it's pretty much the same. Now, the electrical design, which is the tuning of a filter, is not explored in detail in this webinar. We will talk about it, but it is not the purpose of this webinar. Now, if you want to learn about the electrical design of a filter, I strongly suggest that you review a previous webinar by Chris Duffy, which is an engineer, an EasyPower engineer. And here's the link. Here you have the link. If you cannot access it, you cannot copy, you can watch it on your smartphone following the link of this QR code. It's a very good webinar, and it will teach you what this webinar will not. Now, I take that most of you are electrical engineers. You're familiar with how a filter works, but let's review some concepts. A harmonic filter is a combination of capacitors, inductors, and sometimes, not necessarily, resistors. In a filter design, resistance can even be left out, tuned to a certain frequency, preventing harmonic currents of flowing into the system. Instead, harmonic currents will flow into the filter. Now, what type of filters can we construct? Many, many types. What we see the most in power systems are the notch filters, the first order, second order, and C-type filters. You can even have multiple harmonic frequencies in one filter. There are many interesting papers in the IEEE Explorer about multiple frequency filters, but they are far beyond the scope of this webinar. Now, this is a screenshot for EasyPower in which you can see that when you get a filter, which is here, you place a filter. You can select the type of filter that you need. Notch, which is just a combination of a reactor and a capacitor. This is the most widely used filter. First order, capacitor and resistor. Second order, these are used in steel industry. And third order filters. It's a very complete design list of what you can do. Obviously, as you add more and more elements, you get more and more input from EasyPower. But let's begin with the easiest. So the IEEE standard, as most of them, has a very extensive reference list. Here's the standard. And you can see that there's a whole page of references. There's a whole lot of them. But I think that the most interesting references in this standard are these four, which are the 1036, which is the Guide for Application of Shunt Power Capacitors. This standard is very valuable because it gives recommendations on the setup of the capacitors and the filters, which is when to connect in delta, when to connect in Y, when to connect any other configuration. It's very valuable. Now this one, the Guide for the Protection of Shunt Capacitor Banks, has many guidelines that become very relevant when you're designing a filter. How should you protect the filter or the bank? Now, this standard will come into the presentation many times because it is not an application standard, it is a manufacturing standard. Any capacitor that is sold as approved by this IEEE standard will have some common characteristics, which will come in handy at the time of the design. And this is the center book, the most important book in harmonic control for power systems. This is a very widely known standard, the 1992, and it gives the limits for harmonic content on the system. I see that there are some raised hands, but let's hold the questions until the end of the webinar, please. I will gladly answer them. Now, this is some kind of index. This is some sort of index for the IEEE standard, and it's divided in three big parts: the general design considerations, then you go to low voltage filters, and then medium voltage and high voltage filters. But when you understand this is pretty much the same. Now, when you are trying to design a filter, you have to go into the general design configurations, which are the filter sizing, which will come in a minute, the configuration, the tuning, the harmonic content of the filter that it has to support, and the general system conditions, emergency conditions, normal conditions, let's say backup conditions. And then we go to the specifics of the filter, which are the components, the capacitors, reactors, contactors, fuses, breakers, and the suggested connection types. Now, let's go into the first. And I will make a sort of checklist to review when we're trying to design a filter. So this is the procedure, more or less, that we were talking about. Now, the first step for a filter is to ask, what do you need the filter for? The most common application of filters in power systems is harmonic filtering, obviously, but it is also power factor correction. Since the filter includes capacitors, they will provide reactive power, and they will compensate for reactive power consumption in the system. Now, where do we get the reactive power considerations? They usually come from a power flow study, and of course, EasyPower. I made a very simple example to show how to size a filter. This is a plant, a very generic plant, which could be any plant. It has 115 kilovolts PCC, which is point of common coupling. It has a 6 MVA transformer, and then it has a 13.8 kV bus. Now, you may have downstream many transformers, as much as you want, but for the sake of simplicity, I just included one transformer, which is feeding a non-linear load. This load is configured for the main harmonics in a power system, which, as I'm sure you know, are the 5th, 7, 11, and 13. These are the most common harmonics in a power system, industrial power system. And these percentages are typical for a harmonic load, an industrial load, and they go lower as the harmonic goes higher. This is very typical, and it's just an example. Now, here we have a 2000 HP induction motor, which goes into the medium voltage bus. It could very well be a mill or a compressor. I've seen very big compressors on medium voltage. I'm sorry. Now, EasyPower has, even though you cannot specify the harmonics for this particular motor, EasyPower gives a harmonic spectrum, which is traditional, which is conservative for a rotating machine. We'll see it in a minute. Now, these are all filters which are here to teach us how a filter works. Filter 1 and filter 2 are the exact same thing, but I'm going to go there in a minute. Now, this is a capacitor bank. And let's say that we made a power flow study, and the studies of the power flow were this. The results of the power flow study were this harmonic load and this motor, and that's it. So now we run the power flow simulation. And what do we have? We have that at the PCC, the point of common coupling, the plant is consuming 2,200 kVAr. And we have a lagging power factor of 0.82. Now, I don't know if where you live, the utility will charge you for a low power factor, but in Mexico, they most certainly will, and it's very expensive. With a 0.82 power factor, you are looking at a fine of around 7–8% of your total billing. It's very expensive. So this is an urgent problem that we need to correct, and therefore an engineer is commissioned that says, fix this problem. Okay, so now I need to reverse or to neutralize this reactive power flow. So the solution might be pretty easy, and then you say, okay, I'm going to install a capacitor bank. The capacitor bank, and then we energize the bank, which is giving 2,400 kVAr. And then, of course, now the plant is not consuming reactive power. It is providing reactive power to the grid. And we have a capacitive power factor beyond 1. So the economic problem is now solved. In your monthly receipt, the utility will even give you, at least in Mexico, a little bonus for having a high power factor. So that may seem to be the end of it. But if we look at the problem from another focus, using the harmonic analysis, we're going to find something very different. Let's say this is our original scenario, which only contemplates the load and the motor. We have, just give me 1 second. There it is. Now, we have some harmonic distortion in the middle voltage bus. Now, I'm sorry. There it is. Now, we have some voltage distortion in the low voltage bus, which is to be expected because it's where the most harmonic load is. We have some harmonic distortion on the medium voltage bus. And that's it. So if we energize that capacitor, the voltage distortion, which is the THD, total harmonic distortion, goes way up, 3 times as high. And that's not good because all the equipment that is connected to that bus will receive a harmonic voltage, a voltage with a lot of distortion. So now we see that this problem cannot be solved by a capacitor bank. Now, why does this happen? When we run an analysis on this bus, on the middle voltage bus, and we make a frequency scan, which is the impedance against the harmonic value, the frequency, we see that it's linear. It's just inductance, which is transformer, cables, and whatnot. Everything is inductive in a power system. So when we add a capacitor, that bus will have a resonance point. And everything that is inside this curve, any harmonic that is inside this curve, will be amplified. And that is a common misconception because sometimes people say that capacitors produce harmonics, and that's not true. Capacitors do not produce harmonics. They only amplify harmonics. And you can see that in here. This is a very, very valuable tool for checking out how your system will react to harmonic resonance. I see here that the most important harmonics, which are the 5th and the 7th, and everything in between, will be amplified. 11 and 13, not so much. So that's not a solution. And then you hire an engineer and you say, okay, the solution is not a capacitor. The solution is going to be a filter. So how do we tune this filter? That is not the purpose of this webinar. But it's very easy. I just need this Excel spreadsheet. It's a very, very simple spreadsheet, and it helps me tune the filters. So filter 1 and filter 2, for the purpose of this webinar, are identical. Let me prove it to you. I'm going to energize this filter, and then I'm going to check on the medium voltage bus. This filter is tuned to the 5th harmonic. Everything in here will be amplified, but it's not a big deal because we don't have 3rd or 4th harmonics in the system. The 5th harmonic appears as a short circuit, and therefore, look, there's the impedance, very low impedance at the 5th harmonic, so the filter will draw all the 5th harmonic current from the system. Now, this filter is also tuned to the 5th harmonic. It's the exact same filter. Now, you can construct a filter with a reactor and a capacitor, or you can construct the filter using the integrated filter feature used in EasyPower, which is this one. You just take the filter and place it, and then you specify the filter. What do you need to specify for a filter? You need only to know the inductive reactance, the nameplate capacitance, and the nameplate voltage for the capacitors. You may or you may not include the resistance of the inductor in the calculations. It really doesn't matter that much in my experience. So these two filters are the same. Now, the filter has been specified. We need a 5th harmonic filter, and that's it. Here it is. Oh, sorry. My 5th harmonic filter, there it is. Now, we go to the next problem. How do we build it? We need to specify a filter that will keep the voltage rise on the system under 2-3%. This is per IEEE recommendation. So let's check the voltage in PU per unit, and when we engage this filter, the voltage will go up 3%. 3%. So we have a go. This is a good filter. Now, IEEE standard 519 recommends that the buses have a lower distortion than 5%. That's the ideal situation. So if we don't have the filter, our bus has a 5.92% distortion. It's not that high. It's not that high. but it's a little above the standard. So when I place my filter, distortion will go down. This is the best situation. So the filter is the way to go. If we place the capacitor, bad things will happen. If we place the filter, good things will happen. So far so good. IEEE, this is not a standard for harmonics. These are standards for transformers, the C57.12. And the recommendation is that a fully loaded transformer should not have a current distortion above 5%. So let's see how we are doing in that department. If we don't have a filter, the harmonic distortion, the current harmonic distortion in the transformer is well above 10%. Not so good. But then again, this transformer is not fully loaded, and no transformer should be fully loaded. They should be running about 80% of the load. So when we add a filter, the harmonic current is not flowing through the transformer. It is flowing through the filter, which is a nice thing. So we have to watch out for the capacitor heating capabilities in our filter, and this is one of the most critical things in all of the design. So the filter can be configured in many, many ways. It can be done as a Y, as a delta, or as a combination of both, and they can all be tuned to the same frequency. I'm not going to discuss why this filter should be used, or this one, or this one. You should, if you want to know that, please refer to, to this standard, 1036-9092. In this standard, you will find in detail what's this for, what's this for, and what's this for. So the capacitor heating limit is a very relevant thing to consider. Now, according to this standard, which is again a manufacturing standard, not an application standard, all capacitors should be able to withstand a 10% increase of the RMS voltage, a 20% increase of the peak voltage without suffering any damage. And when you overload a capacitor, not overload, when you place a capacitor with an overvoltage, a 10% overvoltage, it will give more reactive power. The relationship between the voltage and the power is squared. So when you square that 10% and then add a 15% tolerance, which is also in this standard, you get a 135% of rated kVAr, and therefore the nominal RMS current. Your capacitors should be, if well manufactured, able to withstand 10% increase in voltage and a 35% increase in power output. Now, this is very important. Capacitors rated for banks are normally not well suited for harmonic filters. So if you have a capacitor bank already installed, like this one, and then you want to convert it into a filter, you will most likely not be able to. Why? These capacitors are rated at 30.8 kV, and so is the bus, so there should be no problem. But this is a very interesting thing that happens when you add a reactor in series with a capacitor. The voltage doesn't drop, it goes up. And the reason of that is because the capacitive current, which has a negative imaginary part going through an inductive reactance, will give to a voltage rise. It's not the most intuitive thing in the world, but it happens. And let me show you. This is the reason I constructed this filter as this. Check out the voltage. The bus voltage is 13.39. And then when I energize the filter, I will have an internal voltage in the filter of 14.37 kV. And this one is well beyond the recommended 10% increase for these capacitors. Now check out, in this volt bus I have a smaller voltage than in this bus. So if I try to use these capacitors into my filter, they will not work. They will most likely explode. So that is one thing to consider when you're designing a filter. Check out the voltage rating for the capacitors. And if you have EasyPower, well, all the best, because you can make this very simple exercise and determine how much voltage you need to hold. So EasyPower really is a valuable tool. So when you overload a capacitor with voltage, it will output more reactive power, therefore more current, therefore more heating. That is obvious from this example, but something that is not quite as obvious is that when you have high harmonic content, which you already have because you're installing a filter, those harmonics will heat the filter beyond the main frequency. You will have third harmonic frequency heating, fifth harmonic frequency heating, and we can see in EasyPower that the voltage, because of that harmonic, will be above the rated voltage for the main frequency. Let's see, when we go into the harmonic focus and we make an analysis of the filter, and I want to evaluate this, the root sum squared voltage, which is the voltage including all harmonics. It's a little over 1 because I have very little harmonics in the system. But check this out. These loads only draw harmonic current. They do not draw power. 0 megawatts, 0 and 0. They are just intended for harmonic current. This is a teaching purpose. So when I go again into my focus and I enable the filter, check this out. This voltage, which is the root sum squared of the voltage. Because I have very little harmonics in my system, the voltage rise due to harmonics is low. But when I start injecting harmonic current into the system, the voltage, the harmonic voltage goes up. Now we have 1% above. So you may not want to take the voltage level of the capacitors to the limit. You may want to design a little above as for the harmonic voltage rise. When I remove the harmonic load, the harmonic voltage rise decreases. So you may want to watch out for that. Now, returning to the checklist, what are the normal system conditions? The characteristic harmonics. You may even find uncharacteristic harmonics, which are background noise. Sometimes it happens. The background and the future loads, it's not the same to design for a system that will not change and design for a system that will grow over time. You have to take that in mind. Now, the IEEE standard has a recommendation that the system voltage variation is in the 5% range during normal operation, and during no load the system may go up to 10% increase, which is the suggested limit for the capacitors. Now, system frequency variations are extremely rare when you're connected to the grid, but they may happen when you are connected to an individual power source, such as a generator in your plant. You may want to watch out because a change in frequency will change the response of the filter, and it may do more harm than it's intended to relieve. Now, are there any system configuration changes? Are the transformers going to change? The main feeder is going to change? Are there going to be any more harmonic loads? When you design a filter, you have to be aware of all of these things. Changes in the system source. Sometimes the utility doesn't tell us, unless you're a very big customer and the utility changes its short circuit level or the XR relationship at the PCC, and then the filter may have a different response in your system than it is intended to. So if the utility is making big changes, they should notify you. Okay. What are the contingency conditions for the filter? Those are the normal conditions for the filter, the ones that we talk about. And the contingency conditions are the switching. The IEEE standard recommends that you avoid simultaneous energization of the filters. If you have more than one filter on a bus, you may want to switch them not at the same time, because it gives a very severe voltage transient, very severe. You have to watch out for transformer energization over voltages. When you are re-energizing a transformer, you may want to check that all the filters that are downstream that transformer are disconnected. Otherwise, when a transformer is energized, there may be a transient over voltage, which can be very severe, and it can damage the filters. Now, when a capacitor or a filter is switched on and off, we must give the capacitors time to discharge. This is also included in the IEEE standard for capacitors. When they are intended for low voltage use, they need to have a discharge medium, typically a resistance, that will get them to 50 volts in under a minute. And for medium voltage or high voltage, they need to be 5 minutes to get them under 50 volts. Now, you may have a situation when you have multiple filters on a bus, and that's fine. You just have to avoid the simultaneous energization, and you have to be aware that because of tolerance, and we'll get to it in a minute, the impedance on every filter most certainly will not be the same. So the filter with the lowest impedance will have most current, and you have to be aware of that, because you don't want to overstress your components with too much current. Are there any unknown harmonic sources in the system? They most certainly will. It's very hard to make a study that includes every harmonic source, so you have to be careful and over-design the filter. Now, the system configuration changes under contingency conditions is when an emergency generator goes up. We have to be aware. Now, that's it. We're going to go in full to the components of the low voltage filter. In my EasyPower example, I have a low voltage filter. And before we go further, I want you to notice something. In this filter, in the medium voltage bus, is tuned to the 5th harmonic. And this is wrong. I'm going to explain why, but this is wrong. And the low voltage filter is meant to filter 5th harmonic. They will sell this filter to you as a 5th harmonic filter. They will sell it to you that way. But it is not a 5th harmonic filter. It's down, and I'll get to it in a minute. Now, if this photo is property of any of the participants, I am sorry, but this is the very best picture that I could find. It has a fantastic resolution, and it shows a very well-made filter. Now, these are the components of the filter. These are the reactors. Those are the reactors. These are the capacitors. You may see that there is more than one capacitor per step. These are this is the switching gear, the contactors, the fuses, and the main breaker, and the whole casing. And it has a fan, a little fan on the door. Now, this is a very, very well-made filter. The most important component of the filter are the capacitors. As we already said, you have to be aware that the rated voltage for the capacitors needs to be higher than the bus voltage. So when you're designing a low voltage filter, you do not want to buy 480 volts capacitor for a 480 volts bus. You will want to buy 525 volts. This is very typical, very, very typical, at least in Mexico, to find capacitors for this voltage for this bus. Now, the capacitors must have a discharge means as to reduce the capacitor voltage to less than 50 volts within a minute of de-energization. This It's included in the IEEE standard, and it's also in the National Fire Protection Association, the NEC. Now, the next component, the reactor, on low voltage filters, they are typically, or almost always, dry type iron core, laminated core, of course. These are called detuned reactors. Detuned reactors. And when you buy a low voltage filter, you might find that the vendor doesn't specify the harmonic of the filter. It doesn't say 5th harmonic or 7th harmonic, whatnot. Usually in low voltage, they are specified as detuning factor. Now, detuning factor is a direct relationship to the harmonic content. Most of the filters that I've encountered have a detuning factor of 7%, and that means that the tuning harmonic is 3.78. As you can see in this EasyPower example, the tuning harmonic for this filter is around 3.78. That is what you would normally find in a low voltage filter. And I'm going to return to this a couple of times. Now, when you have a noisy reactor, the most probable cause is that the core is not properly clamped, because AC current makes the lamination vibrates, and the harmonic content makes the vibrations even faster. The nuts and the bolts of this core may go unclamped, and that means that the reactor will make a lot of noise, and that scares the clients when the reactor is making a lot of noise. And the most probable cause, in my experience, is that it's not properly clamped. The reactor specification is largely the manufacturer responsibility, and it has to be a combined job of the power engineer that makes the specification for the filter and the manufacturer. The manufacturer should receive the harmonic spectrum expected for the filter. Why? Because the core of the reactor is extremely sensitive to harmonic content when it regards loss, therefore heating. The reactors are very sensitive to heating because of harmonic content, because in the core you have eddy component, an eddy power loss, and they go bigger with bigger frequencies, and when you expect harmonic frequencies to flow into the reactor, they will overheat the reactor because of eddy core losses. So the reactor should be prepared for it. Now, how do you provide the manufacturer with a harmonic spectrum? Of course, using EasyPower. Let's say that we made the system, and then we want to specify this reactor, the CLR1. You must send the manufacturer this, the expected harmonic spectrum of the filter. So it really is very simple. You only take this and copy to an Excel file, and that's it. That's what the manufacturer expects to receive, as to design the reactor specifically for that harmonic spectrum. Now, the reactor should be protected for overheating, because it is the main failure of the reactor, overheating. Now, you should install a thermal cutout, which is a resistor that changes with temperature, near the hot spot. And where is the hot spot in a filter? Who knows? You have to make a thermal imaging when the filter is running, so to see where the hot spot is, and then install the proper protection for high temperature. It is the main reason a reactor fails. Now, this is very interesting. The capacitors and the reactors have a tolerance. Everything that is manufactured has a tolerance. So this standard limits the capacitor tolerance to -0% to +10%. There is no defined standard for the reactors. So care should be exercised, because the capacitor and reactor tolerance can detune the filter. the tuning the real frequency, the tuning frequency for the filter is the nominal tuning frequency times that formula. So when you evaluate it using Excel, for example, you may find that a filter that is tuned to the 4.7 harmonic, because of the tolerance of the reactor and the capacitor, it can go all the way down to 4.18, or it can go all the way up to 4.95. So you have to be careful of the tolerance. If you design a filter with a very, very specific tuning, the most likely thing that will happen is that it will not work as intended. So you have to watch out for this. Now, this is critical. The standard says low voltage filters, but I added this, any filter are often tuned below the nominal frequency because as time goes by, capacitors will lose capacitance. So the impedance curve will move to the right. And what was originally intended to filter the fifth harmonic will end up filtering the harmonic 5.7. But it will amplify the fifth harmonic, therefore doing more harm than good. You have to place the filter below. Tuning a harmonic filter more sharply than required will draw more current. Check this out. Check this out. When I run the power flow, this filter is tuned precisely to the fifth harmonic, and it draws 95.89 amps. But that's not the best thing to do. You want to tune this filter, let's say a little below, 92%. So I'm going to tune this filter right there. And now the filter, the filter is tuned a little below the fifth, 4.7, 4.6. Yes, 4.6. And that is the best way to do it. And when we run the power flow, the current went down almost 2 amps. It may not sound like much, but remember this is medium voltage, so every amp counts. The current goes down. So the reactor and the capacitors are less stressed than if the filter was tuned to the fifth harmonic, a precise filtering. Now, remember that the reactors and the capacitors have tolerance. So you have to account for it. And when a capacitor fails, it short circuits, and it may change the whole tuning of the filter. Now, the contactors should be IEEE or NEMA rated, UL listed, and you have to watch out for the maximum system voltage, including harmonic overvoltage, the continuous current, including harmonic content, and the number of switching operations. As I said before, the switching of a filter is less severe than the switching of a capacitor bank. So the contactors do not need to be as robust, but they need to be designed for capacitor switching duty. Now, the fuses may be exchanged for a circuit breaker, but they should not be exchanged for thermal overload devices. Remember, the purpose of the fuse is not to protect from overload. It is to fuses protect from short circuit, not overload. So you should have both types. You need a fuse to protect from short circuit and a thermal overload to protect precisely from thermal overload. Or you may have a breaker. So the rated current for the fuse should be at least 2 times the capacitor rated current. Capacitors have a high inverse current. The voltage rating should be according to the bus, the filter. Now, sometimes capacitors will have internal fuses, but they should not be used as means of primary protection. You need another means of protection for the whole filter, not for just the capacitors. And in the filter with more than one capacitor per reactor, each capacitor should be individually fused. For example, in this filter, in this beautiful filter, we have, I think there are 6 capacitors per reactor. 6, and each and every one of them should have an individual fuse, and then you need a fuse upstream, and then a main disconnecting device. These are all the recommendations of the IEEE standard. The circuit breaker really has no specific recommendations. You just have to watch out for the maximum system voltage, the harmonic spectrum for the over voltage and the over current. Check out the interrupting rating, which is the short circuit rating for the bus, and the frequency of operations. Now, the standard has some recommendations for the connections and building of the filter. I did not include these because they are common sense. Connections should be tight, connections should be the correct size, the building of the filter should be clean, should be in an orderly fashion, the case should be NEMA rated according to the environment it's going to be in, waterproof, NEMA 1R, NEMA 3R, or whatever. These are very short recommendations in the standard. And the point of connection, this is a very important thing to consider when designing a filter. Where are you going to connect the filter? You can connect the filter in every load that has a harmonic content. You can connect the filter in the distribution bus, which is the most common practice. For example, you could have many loads on this bus, and you could place a filter in every load. You may place the filter in the distribution bus. Now, if you decide to include a filter with every load, there are some advantages because the filter provides reactive power and absorbs harmonics. The feeder system doesn't have to be as big. You expect less current in your transformer and your cables and everything. Therefore, with less current, you have less system losses, which is a good thing. Now, the voltage distortion at the point of utilization is minimized because the filter is there to filter harmonics before they go into the system. The filter can be sized specifically for the load, and it can be switched on and off with the load, preventing overvoltage in the system when the load goes out. Obviously, if you include a filter with each load, it's going to be extremely expensive. So it's not the best solution. Now, if your concern is harmonic filtering, you may need to place a filter on each load. If your intention, your main concern, is power factor correction as it normally is, the best practice is to place the filter in the distribution bus. If you are going to place the filter in medium voltage or high voltage, you need to watch out for the harmonic current from the source. We tend to overlook that the utility can include harmonic content. And if you place a filter, and a poorly designed filter, let's say at the 5th harmonic, a very precise tuning at the 5th harmonic, that filter will draw a lot of harmonic current, not from your plant, well, from your plant, but from the utility as well. Therefore, it can overheat. You also want to watch out for overvoltage, because if you're in a utility ring where there are many customers, and those customers each has a filter or a capacitor at the PCC, you will have an overvoltage. And if the load of any of those plants goes out, the overvoltage will be more severe. So I guess that's it. That's the end of the IEEE standard. We're lacking the medium voltage, but it's not the scope of this webinar. So this is my email. If you need anything, if you want to ask me anything, please feel free. If you want to have a more personal conversation, we can also talk on Skype. This is how you will find me, and I will gladly talk with you. I'm at your service. If you need anything, I'll be happy. If there are no further questions, I think it's time to end the webinar. It's been a real pleasure talking to you. Thank you very much for all your questions and your time. And should you need anything, please contact EasyPower or myself. Thank you very much. Bye.